Hey everyone, welcome back. This is lecture 16. We're going to talk about learning theory, about all these kinds of formal mathematical ways we can try to get an idea of just how good or bad our learning systems are going to do. Well, before we get into that, let's go ahead and talk about some course logistics, because my, do we have a lot of logistics coming. Kind of took me by surprise this week when I realized just how close everything was. So hopefully you've already seen on Piazza that homework number 4, I've delayed the due date. So instead of having it be done 15 minutes ago, you now have until Sunday, which is November the 15th at 11:59 p.m. I heard some people were struggling with a lot of other stuff, and to be honest, nobody was going to be marking it over this weekend anyway, so go for it. Get some extra time. Then we also need to get you information on your final project. So I'm going to release a detailed packet. Pretty sure it'll be this weekend. If not, it's going to be Monday. But that's okay because I'm sure that you're all busy stressing about the midterm. So midterm number 2 is a week from this Friday, so it's going to be November the 20th. And we are going to have a review lecture once again on Monday the 16th. So this coming Monday, just a few days from now, will be a review lecture. Now, the last bit of stuff is good news. As you may recall from the syllabus, there's been this guest lecture slot that's been hanging around. Well, I found somebody pretty awesome to fill it. Eugene Izhikevich is he's a rather interesting fellow who's gone from mathematician to computational neuroscientist, looking at understanding how the brain does learning and represents various things going on. And then he decided, that was too boring. I'm going to go start a big company that's going to both do computational neuroscience on the one hand to try to come up with amazing AI, and on the other hand, we're just going to make a bunch of cool robots that companies are going to hire to clean things and move stuff around factories and that kind of thing. So I think we're pretty lucky to get him to come in, and he's going to be able to speak both a little bit about some kind of cool technical stuff that they do, and also he'll be, giving you his perspective on machine learning careers, both as somebody who's, from your standpoint and also from the standpoint of somebody who's hiring somebody like you. So I'm sure that will be very useful. All right. So that's enough of that. Let's talk about learning theory. Okay. So math is nice. Math isn't just about how do these algorithms work, but we'd also like to know things about them, like how good can they be? What kinds of guarantees do we have about the performance of a given algorithm on a given data set? So common questions that get asked are things like, how many different patterns could we store in this neural network? What kinds of guarantees can we get about the stability of this algorithm? Will it always converge to a solution, or will it sometimes blow up and not provide one? So there's all kinds of branches of learning theory which deal with questions like that. Today we're going to discuss 2 particular branches that are kind of related: probably approximately correct theory and statistical learning theory. Now, statistical learning theory has very strong links to support vector machines, and the PAC stuff, the probably approximately correct, is very interesting because it's a highly general theory. It's not linked to a particular form of a classifier or regressor very much, And that gives it an interesting broadness, even at the same time as it gives it an interesting weakness. So we'll get more into that as we go. But just to give you a kind of a taster, the kinds of questions we're going to ask are below. Given a particular classifier type, which has known training error on n samples, how likely is it to have a small generalization error? Or will it maybe just, be crud on generalizing to new data? Or equivalently, we can flip that question around and ask, given a desired generalization error rate, how many samples do we probably need to achieve that error rate? Okay. Well, let's get into the nitty-gritty and see what that would look like. So, there we go. So let's take a look at the infrastructure that we need to address these learning theories. So both PAC and SLT, probably approximately correct, and statistical learning therapy. Yeah, I need some therapy. Statistical learning theory. They both come from the same framework, where we need to kind of define the problem. And this will be familiar because this whole time we've been defining supervised learning in a similar way. So there's some sort of data source, okay? Something that generates data, and that has a particular statistical distribution. And from that distribution, we're going to draw samples, okay? So on the left here, this is the idea that there's some underlying process that we're interested in, which is generating data. Okay? And that data is got a random component to it. So there's an underlying process which is deterministic, but there's some randomness lying on top of that, some measurement error which has a random component, say, would be a typical way of understanding that. So this distribution here has this form here. We're going to say that we draw data X from a distribution P star, okay? P star is this underlying distribution, and we're going to draw I samples. We're going to draw all I samples from that. All right? Now, this data goes to some kind of expert, an oracle, a magic thing which generates labeled training examples. This expert or supernatural oracle or whatever is got the ability to correctly label every single data point as belonging to class A or class B or however many classes we're working with. All right? So the oracle labels each instance, each X, with an unknown function C star. The C stands for concept class. So there is some concept that we are trying to learn with our algorithm. That's the idea here. Now, what that concept is, how we get a hold of it, well, we can see the labels the oracle produces, or more likely the labels that some poor graduate student generated on all this data, right? But our machine's job is to take those labels and figure out how to label brand new data, okay? So we pass, just like we've been talking about in supervised learning theory this whole time, we pass a set of each X with the corresponding label coming from the expert. Now again, the expert was using a concept to produce these labels. The expert can look at any new data point and correctly label it. Our learning algorithm can't do that yet. It's just going to try to learn the right concept given what it sees here in the combinations of input data and correct concept for each sample of the data. All right, well, now we get to the exciting part. Our learning algorithm has to choose a hypothesis, which is going to make its error on this training set as low as possible, right? just supervised learning. We're going to try to minimize our error on this training set. All right, so out of that argmin, okay, so we're going to get a hypothesis is how we're couching this, right? So the hypothesis is maybe more familiar to you as the function which takes inputs and transforms them into a prediction, okay? The hypothesis is essentially the weight vector, right, given the form of the algorithm. So the hypothesis that we're talking about could be any kind of classifier, right? The hypothesis is both a structure, like a linear discriminant, and also the particular weight values that are used to set where that line lies, okay? So the learning algorithm's job is to pick the right hypothesis to best label the data to reduce training set error. Super familiar stuff, I know, but I'm just going to run through it here because it has some slightly different ways of looking at it, okay? So important here to note is that the training error is this R hat, and H hat is our hypothesis. So just generically in statistics, if you're not already familiar, the hat, this thing, right? If I wrote X hat, that hat just that was right behind my own face. So whatever I write, this hat, that's something that stands for an estimate, okay? This is an estimated value. It's our estimated hypothesis, and it's our estimated training error. All right. So let's take a look at this as kind of a Venn diagram, right? We have first off our instance space, X. However many variables there are, whatever potential values those variables could ever take, that is our instance space. The X's up here have to live inside that space. Now, we can narrow that down because likely our data comes from a fixed distribution which can't take all values of the instance space, right? So if our data is real numbers, it's probably unlikely that our data bridges everything from minus infinity to plus infinity, right? So some smaller chunk of the instance space is bridged by our data distribution, which on the one hand, we called it D over here on the slide I grabbed from somebody else, and over here we called it P, right? But there's an underlying distribution which we're drawing from. So it's either this P star or it's D according to our notation. And when we make a random draw out of that data, we get a training set, right? We get a bunch of X's. All right. Now, our Oracle knows, some stuff. It knows how to label these. So it says everything inside this orange box belongs to the positive class, and everything outside it doesn't. So everything inside is a 1, right? Oops. Everything inside is a 1, and everything outside is a 0. Well, we're not done yet because our learning algorithm tries to come up with some way to learn this unknown function, right? It can only observe the labels. It doesn't know what the Oracle was doing to make those labels. So we look at that same data and we come up with this H hat, which is a hypothesis that labels everything inside the blue box as a positive class. So this labels everything as a 1 inside and everything outside as a 0. All right. So quantities we care about. So the true error, we're going to denote R sub H. Whatever the hypothesis H is that we are using to make this blue box, right? However, we're drawing our decision boundary. That's our hypothesis, is where our decision boundary is, okay? So however we're drawing our decision boundary, that is going to give us a particular error on the whole population, right? We're never going to see the whole population. We're only going to see a random sample. So inherently, this true error, this R sub h, is unknown, okay? This is always an unknown quantity because we never see the whole population. We're only going to be able to guess at it. So this is, in a sense, something we can never know, but that we can guesstimate, all right? And we can guesstimate it by taking a look at the training error. So this is our R hat. R hat is going to be, we can always calculate it based on the training data. And that's defined as the probability, once we draw this sample, right, that the hypothesis we give for a given data point is not matching what the oracle says should be true. And that generates a 0-1 loss function that we're quite familiar with at this point. Okay, so recall that, again, what we want to find out is this true class concept, this C star, right? We want to get after this thing right here. We want our outputs to match that. So the expected risk minimizer is what we really want. We want to minimize our generalization error. We want to minimize the true error on the whole population, which we can never observe, so we can never do this directly, right? So instead, we're usually going to settle, just like always in supervised learning, we're going to settle for fitting ourselves to the training set. That's all we got. All right, so far, so good. So let's take a look at this whole PAC learning. Probably approximately correct. So PAC learning asks the question, can we bound the true error, right? This is the true error using our training error. All right? Well, I'm spoiler alerting you. Yes, we can. Okay? So what does PAC stand for? All right, I've already said it several times. Probably approximately correct, right? So what does that mean? Well, so the approximately part means we're going to try to get R sub h towards 0. Okay, we can't ever know R sub h, but maybe we can use some tricks to say we're going to get close to 0 R sub h. And we're going to do that with high probability. So we're going to say that the probability that we approach that 0 is going to get close to 1. That's the bounds we're looking for, that we're approximately correct with high probability. So formally, the way we're going to define this is we're going to say that what we're after is the probability that for all hypotheses that our classifier can generate, so it doesn't matter what we actually learn in detail, right? As long as all the hypotheses that it can generate, that we can do this, that we can guarantee that the difference between our true and training error, right? That's the delta from true minus train, okay? That we can bound it by this epsilon, okay? So that is less than some number, and we can set that number to be arbitrarily small, okay? Then we not only want to do that, but we know that there's some probabilities here, right? There's something random. So we want to make sure that all this happens with a probability that's small. So when delta is a small number, then 1 minus delta is a number that's close to 1. So we're getting there with high probability. All right? So let's go on. So what's the random thing here, right? The question is asking, where does this random noise come from? That we have to do anything with a delta of probability. Well, the data distribution is being sampled, and that's the source of our randomness. Every single draw from that data distribution will be a little different, and that means that when we estimate something, right, that it's not necessarily going to be exactly the same for every draw of the sample. Okay, so we're after the true hypothesis, right? Sorry, the true error that our algorithm can learn to do with a given hypothesis, and we're bounding that true hypothesis as being plus or minus epsilon away from what we get with our random draw. So, finally we get down to the nitty-gritty. What we're going to do with PAC theory is we're going to define something called sample complexity. Sample complexity is the minimum number of samples we need in order to learn to this criteria. In order to learn something which is no more than epsilon away from perfect with a probability that's approaching 1 minus delta. Or sorry, a probability which is better than 1 minus delta. So we can set a delta that is tiny, 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 just a small probability nip away from 1. And we can say we're pretty dang sure that we're going to get at least as close as epsilon away from the best possible result. Okay? So finally, we need to know a few more bits and bobs. So we also need to know that a hypothesis is consistent. The definition of consistent is when the training is consistent with the training data, right? It's consistent in the sense that it's going to generate 0 training error. Our hypothesis can perfectly learn the training set and not make any mistakes. So that is our definition of a consistent hypothesis. All right. Now in the end, everything that's going to come out of this are 4 bounds. What is a bound, right? Well, an upper bound is that we know that the truth has to be underneath us, right? The upper bound for something is that we know it can't be worse than this. All of this stuff is upper bound. All right? Now, another way to do it is you can get a lower bound. We're like, no matter what, we're not going to do worse than this. Okay? No matter what choices we make, as long as we're using the system, it's got to be better. That's the lower bound. All right? And the bounds we're going to look at are for 2 cases. We're going to look for this realizable case, so-called, here, where what that says is that we know for a fact that in the space of hypotheses our machine learning algorithm can try, right? Remember those boxes? We know that our box can move such that it goes over that blue box. Sorry, that the blue box can move over the orange box, right? Yeah, why can't I clear all these? That is annoying. All right, if our blue box here can move over the orange box generated by the oracle and perfectly encompass it, then that is when we have a realizable learning system. Okay? So case 1, realizable learning system. The agnostic case is when we don't know that our hypothesis space can encompass what the oracle's doing. Maybe we have, for some reason, that our box can't move perfectly over it, but it can nip over the side of it, right? Then that's an agnostic case. So the bounds are a little less strict for agnostic, and they're a little more strict for realizable. So we can get closer to the truth with the realizable case, and we have to be further away in the agnostic. Then finally, we have to look for not just 2 cases of what the oracle's doing, but 2 cases for our hypothesis space, for what our machine learning algorithm is doing, right? So sometimes our machine learning algorithm is able to pick out lots of different things. It's able to make lots of different, possible places of that box, but it's not able to do an infinite number of things, right? So something that is countable in the number of hypotheses it can test, right? Or we can have infinite numbers of hypotheses that are actually relatively easy to generate with pretty simple algorithms. So it turns out that we need different math to describe those cases. Now, all right, here we are, 25 minutes into this. Maybe it's time to actually see some sort of guarantee. All right, so this is just a reminder of what we wrote down, that the what we're looking for is that the probability of the difference between truth and what we get on the training error is less than the epsilon, less than that threshold that we're going to pick, okay? And it's going to be less than that threshold with probability, that's the p on the outside, that's greater than 1 minus delta. And delta is a small number, right? Delta is small, epsilon is small, which says our error is bounded inside a tiny ball with high probability. Say the algorithm is consistent, we've already talked about. Consistent if there is always, that we're always able to take the full distribution P and force it to go to 0 for the error, the training error. Okay, so, and we're after this sample complexity. That's the minimum sample size, the minimum n, which gets us to this declaration. Okay, so we're going to do a bunch of math. We're going to get an equation for this, and if it turns out, as it will, that the number n that we need is a polynomial function of eta and delta, then the hypothesis is said to be PAC learnable. Okay. So we need to, like I said, we have 4 cases. We need to talk about, this is what the oracle is doing. Does the oracle's concept within the bounds of the hypothesis space that the machine algorithm can do? And this is what the algo is doing, okay? Is the algorithm able to take on an infinite number of hypotheses, or is it just a large finite number? So we're going to start in here. This is the easiest thing. I'm going to show you a proof. Please don't freak out, okay? I can say that you're not going to end up doing a test where you have to come up with this proof, right out of the top of your head. The important part here is to realize what it looks like to do this kind of work, okay? Because again, what we're after here is finding some bounds on how good a situation we can possibly have. And that seems pretty important, right? If you're doing machine learning, we want to know how good something is. So we're going to start with a theorem, and then we're going to go through the proof of it. Okay? So this is the proof for a realizable finite hypothesis space. Okay? That is that the oracle and the algo can come to the same conclusion, that the algorithm can do it. Okay? And that the algorithm can only take on a finite number of possible hypotheses. Okay, so I'm just going to state out the theorem, right? This n number, this is the number we want, right? We know that if we get n or more samples, that we're going to be able to hit this performance guarantee that for a small eta and for a small delta, we're going to get a number that is pretty dang close to 0 on the generalization error. So here's that proof. Let's start with the opposite. Let's start by assuming there are bad hypotheses. And they're bad in the sense that if you pick that hypothesis, your error is going to be greater than eta. You're going to be too far away from what you want. So you're going to get a true error that is worse than eta. Okay? We're going to say there are k of them. So there's k bad hypotheses, k h1 through h blah, blah, blah. Okay? So let's pick a bad hypothesis. Let's say that the probability that we don't just pick a bad hypothesis, but we need to get, because it's realizable here, right? Because it's realizable, we need to get one which is consistent with the training data. So the bad hypothesis generates bad generalization error, but it perfectly fits the training error. All right? So, and that's inherent in this definition of realizable. Okay? So because it's realizable, we know we do 0 training error. And so we have to look at, well, the probability that a given hypothesis is consistent with the first example has to be less than 1 minus eta, right? So if we only had one sample and we know that we are worse than eta on the generalization error, then we can only do we have to be worse than 1 minus eta on the when we do the first training example, okay? Well, we get worse than that because, of course, we probably don't have just one training sample, okay? So we know that we're going to have n training samples, all right? So the n training samples, let's just take the view that we normally do, that the probability of making a mistake is the same on every training sample, okay? So they are independent. Independent probabilities multiply, right? So for the n training samples, we have 1 minus eta, 1 times 1 minus eta times 1 minus eta. We do that n times because there's n training samples, and they're all linearly independent probabilities. Okay? So that just works out to this. 1 minus eta to the n power. Okay. So again, we're consistent with those n training examples, means that we do 0 error on the training set. Okay. We have to keep marching on with our theorem. So the probability that at least one of these bad hypotheses is consistent with the first n training examples, right? How many hypotheses did we say there were that were bad? Because what we just worked out on step 2 is the probability for a single bad hypothesis. Well, we know we have k bad hypotheses that are out there. All right? So the k hypotheses, let's just going to end up putting a k in front of our 1 minus eta. Okay? Now, the statement here is that there exists some hypothesis such that the true error is bigger than epsilon, and at the same time, the training error is 0. All right? That's an and, right? It's a union. Well, we know that the union of this is less than the probability of the first thing plus the probability of the second thing. Right? And that's how we get to this. All right? So we put the k in front of the 1 minus epsilon to the n, and we know that this k, right, is how many bad hypotheses there are. All right, so the number of bad hypotheses cannot be bigger than the number of hypotheses, right? So if the whole hypothesis space is bad, k and h are the same size, but k can never be bigger than h. And fairly likely that there's at least one or two decent-ish ones in there, not terrible ones. So in many cases, k may be less than h. All right, so just because h, the size of the hypothesis space, is bigger, let's go ahead and use that. It's a looser bound, right? It makes our system looser and less likely to mess up. All right, so we were at this stage right here. We had just converted this into a less than, my iPad is messing up, less than the size of hypothesis times 1 minus epsilon to the nth power. All right, so we're going to get another, we're going to take another thing, we're going to get another looser bound. So we know that something that's to the 1 minus power, 1 minus x, is less than the exponential of minus x, right? So this is a generically true thing that no matter what your x is, 1 minus x is less than exponential of minus x. So we can put an even looser bound on top of this. And that form will have a payoff here in a minute. The reason we're doing that kind of thing is, of course, we're going to end up taking a natural log. All right, so the bound is looser, but it lets us make a calculation, is why we do that. So, all right, so if we're going to calculate these values of n and delta, such that, again, we've gotten down to this form here, right, that the size of the hypothesis exponential of minus epsilon n is less than delta. So we can start doing some fairly simple algebra, and get the delta from this side to the other side, take the exponential over to this side, right? And we start logging things, okay? And once we start logging things, stuff separates out. The natural log of 1 goes away. The natural log of the exponent of minus epsilon n just becomes epsilon n. So finally, we have epsilon n over here. We just move that epsilon over to make 1 over epsilon, and we get to this form that's looking good. That's very close to our theorem, right? But we're still stated in the form of, this is how we get bad stuff, right? This is for our thing to be bad, we need this quantity to be less than n. All right, we need to switch this over and show how to get good, how to get the good algorithms, okay? Oh no, I'm having iPad troubles today. There we go. All right. So we're going to assume statement 1, and then with probability delta, we're going to say that there exists an H in the hypothesis space such that the this true error is bigger than epsilon, right? That's just assuming our statement, and that the training error is 0, right? That's what we have said right here. Okay, is the equivalent of saying this stuff. So for all h, blah, blah, blah. Now to solve this thing, to turn it into the good, we're going to use the contrapositive proof. All right. Now, I'm going to admit to you that I'm just parroting what's written down here, right? This kind of proof thing is, don't worry if it's not your cup of tea. It's not my cup of tea either. If you asked me in 6 months to derive this off the top of my head, I'm probably going to fail, right? Again, I don't want anybody to panic. I'm just walking you through how these proofs work. Okay, so the contrapositive is a way to do a proof where we start with if A implies B, then that tells you that not B implies not A. So we're going to take this A here and this B here, right? So having this be a bad true error implies that the training error is greater than 0. So we're going to turn that around and do the not B, not A thing. So we're going to say having the training error be 0 enables us to have the true error be less than epsilon. Okay, so we went from there to there, and we did it with a flip from greater than epsilon to less than epsilon, and we went from there to there, where we went from greater than 0 to 0. Okay, that's the contrapositive, I guess. Like I said, I'm just reading what's written there. So this implies that if the learner returns a hypothesis with 0 training error and probability 1 minus delta, that H has to be within an epsilon bound of the true error. And that's what we wanted. As they say, QED. Right? All right. As I alluded to, this is difficult, and it's not the main point that I want to get across. What I do want to get across is that we now have a bound, right? We can say from this theory that as long as the number of samples you have is bigger than this quantity, then we know that we can make an arbitrarily close to 0 attempt at the generalization error. And that's powerful, right? That's saying that even though we can never really know the true population, we're going to be confident that we have quite low generalization error. So, important features about this. So, note that this is logarithmic with the size of the hypothesis space and also with the probability. So, even as the hypothesis space grows and grows and grows, the number of samples that we're going to take is sublinearly increasing. All right? So that's good. Even as we get powerful algorithms, we are not going to end up needing arbitrarily huge amounts of data, because the implication is that a powerful algorithm would be able to take on a very large number of hypotheses potentially, right? Think about this in terms of the 9th order polynomial fitting that sine curve versus the linear fit, right? So one of those, I just sketched, right? So if we're fitting data that's supposed to be in a sine, and if we fit a line through this, we're going to get something that looks like that. Okay? That line can only take a few different things here. Well, actually, that's not true. But it can take fewer things than a ninth order polynomial, which can do stuff like this, right? And because of that wiggliness, it can take lots and lots and lots and lots of different things to it. Okay? Right, the other thing here is that it's only polynomial in the epsilon and the delta. So that's good, right? We can get arbitrarily small without getting arbitrarily large n. So pretty cool. All right, so this was all for the realizable case. Again, realizable just means that we get to a training error of 0. Okay, or in the notation we've just been using, r hat of h is equal to 0. All right, well, the agnostic case is, oh, we're not going to get there yet. Sorry, I've got my iPad. Rah! Okay, let's work a quick example. All right. So this is for finite hypothesis space. A hypothesis space that has maybe a large number of possible hypotheses in it, but it's a finite number. Okay, this kind of hypothesis space is actually always going to be super simple. Okay, because most things that are interesting have infinite hypothesis spaces. So what is the kind of the closest thing we can get to a real machine learning algorithm that has a finite hypothesis space? It's conjunctive coding. Conjunctive coding is when we do something like this, where we have logic gates, okay? Where we have x1 and x2 and x3, and that's the pattern I want to learn, okay? Or in this case here, right, in this notation that we're doing, that's x1 and not x3 and x5. Okay, so the 1 minus x3 is a notation that looks like not x3. All right, so, you know, you can imagine doing something with categorical classification with an algorithm like this, right? Which is just learning the ands, right? It's just learning of all these, you know, 10 bits. What's the on-off pattern of the bits that results in this being seen as a bird versus not a bird, or results in this being seen as whatever our positive class is. Right, so it's still a toy problem, but it's not a ridiculously tiny toy problem, right? It's super, super simple. It's simple enough that the hypothesis space is finite, because the number of possible hypotheses of a form like this is just related to the number of bits, or the number of zeros and ones that you've got here, right? So let me show you what I mean, right? So if this is 10 bits, each bit is 0 or 1. And our conjunctive code, it's going to be able to take 3 possibilities for every single bit. We can either say that for a certain bit, we need it to be true, right? Like x1. Okay, we can need it to be a false, like I'm going to say x6 here is false. Okay. Or we can be don't care, which is that I never wrote down x4 here at all. So we don't care what x4's value is. All right. So it can be true, false, or don't care in order to be positive class. All right. So that's the true, false, and don't care are 3 values that each bit can take. There are 10 bits, so there are 3 to the 10th possible hypotheses that we could generate in this instance space. All right, so there we have it. We have actually shown you a nearly interesting version of a finite hypothesis space. Okay, let's just pick our bounds. So we want to make sure that we are, within 1/10 of the correct error. So our true error is no more than 1/10, no more than 0.1. And we hit it with a probability which is 99%, right? It's 1 minus delta. 1 minus delta, where delta is equal to 0.01, is a 99% chance of getting within 0.1 of the 0 generalization error. All right. So here we go. We have a theorem. We can plug numbers into it. And now I ask you to take a minute, press pause, and figure out which one of these answers, A through H, is the correct way to plug in the numbers. I would do the Jeopardy theme song in honor of Alex Trebek dying recently, but yeah, you don't want to hear me hum. So, does everybody's had a chance to work this through? All right. So what do you think it is? Anybody? Bueller? Somebody from the back row. All right, I'm going to force you to give me a part of it then. All right, you in the blue baseball cap. What do we need, right? What do we need for the number of hypotheses, the hypothesis space, right? This stuff, right? So what do we need? We need, yes, 3 to the 10th. That's right. So when we take the natural log of 3 to the 10th, can we pull the power 10th out of it? Yep. Okay, now you've got it. So you're right. We need the 10 times natural log of 3 parts, right? There's several of those. So you can see that this, and sorry, nope, not that one. Fooled myself. Okay, so those are possibilities, 10 times natural log of 3. All right, what's the difference between the two of these? Oh, look. Everything is bad. My iPad is dying. All right, never mind. There's the right answer. There you go. Okay. We're getting kind of past time. I have a few more slides, so I'm going to speed up. So, sample complexity. We did the realizable case. I'm not going to walk you through the agnostic case. Just to remind you that the realizable case is when our training error is 0, and this is when we don't know if it's going to be 0 or not. Okay? If we don't know if it's going to be 0 or not, we have to use a different kind of bound to generate it, which gives us a slightly looser upper bound. So we need a few more samples. Okay? It's not a big deal. They're overall the same kind of form. And again, the important thing about this form is that it's inversely linear in epsilon. So having the error requires double the examples. And it's only logarithmic in h. So quadrupling the hypothesis space only requires double the examples. Okay? So pretty good stuff. It's only a little bit worse with the agnostic. So the next step, because most interesting algorithms are going to be infinite in their hypothesis space. So the next step is to figure out how to define things for an infinite hypothesis space. What is the size of the hypothesis space if it's infinite? Boom. Well, so we're going to do something a little bit different, right? Because like I said, all the interesting ones, including linear decision boundaries, are infinite. Why is a linear decision boundary an infinite hypothesis space? Well, you can have an infinite number of slopes and intercepts. Okay? Right? They're real numbers, slope and intercept. So therefore, there's an infinite number of them. It's trivially true. And it's true even for lesser things than linear separators, linear decision boundaries. Just for a threshold, moving like where the perceptron's threshold is at W over B, same deal. There's an infinite number of things on the real line. Okay. So anything like this is going to be, which is going to be part of all realistic machine learning algorithms, is going to be infinite in hypothesis space. So this is where we get to Vapnik-Chervonenkis, or if I can put on my pretend Eastern European accent for a minute, Vapnik-Chervonenkis. So this VC dimension by the authors Vapnik and Chervonenkis is a definition of a hypothesis space. This is cardinality in terms of the largest set S that it can perfectly separate. Okay, that is what it means to shatter. So the H sub S is the set of splittings of data set S using concepts from H. Okay, to make it more clear, if we're going back to that picture of boxes of a hypothesis space, all right? If we want to put all the positive examples inside the box and all the negative examples outside, all right? Now our hypothesis, whatever it's going to be, has separated out positive and negatives, but it needs to do that for every possible pair of points in this space, all right? So if we undo this one and make this one not positive but negative and make that one positive, can our same shaped decision boundary be redrawn to do that? Okay, so now we have, oh, yeah, my iPad's freaking out. Okay, so as long as we can split any pair of points away from each other with our decision boundary, then we can do what's called shattering the space. Okay, so a set of points S is shattered by H when those hypotheses split S into all of the 2 to the S possible ways. Okay, so what we've done here, is we've gone from countably numbered hypothesis spaces like the ands, the conjunctive coding, to infinite hypothesis space, but now the way we're going to count how big the hypothesis space could be is not by the hypothesis space, which is infinite, but by the biggest data set it can perfectly split up. So that of all the points that are in there, we can split them up in every pair possible, every single point being a different possibility. Right? So to do that, we need to add in a few more things. So the VC dimension of a hypothesis space is the cardinality. It's the number of data points that can be shattered by h. And again, shattered means that all pairs of points can be separated. So, and if an arbitrarily large set can be shattered by h, then the VC dimension is infinity. Okay, that's just like a definition that you don't have to worry about. So, in other words, what this says is that to show that the dimension of an algorithm is d, then you have to show there exists at least one set of d points that can be shattered. You don't have to show that all sets of d points can be shattered. You have to just show that one of them can. But on the flip side, you have to show that there does not exist a set of d plus 1 points that can be shattered, right? You have to show that at least one of the lower number can be shattered, and you have to show that none of the higher can be shattered. Okay? So let's take a look at this and how this is true, all right? So for the threshold, I'm just going to tell you that the VC dimension is 1. That's saying that any 1 point could fall anywhere on this line. So we could make that 1 point negative, or we can make that 1 point positive. Okay? So we can call it either one of these things. But we can't do 2 points. Why? Because while we can make 2 points both positive, so annoying. All right. Well, we can make 2 points positive and 2 points negative and make them one of each. We can't right, we can pick a set of points where we can't do that, right? Sorry, so I apologize, I got lost. So for this one, while we can do it with these points, if we had 2 points that lied right on top of each other, literally occupying the same space, we could not separate them. Okay? So yeah. All right. So for intervals on the real line, we have that the VC dimension is 2. So we can take an interval and go around, or we can do that, right? That's the positives. Or we can do that, right? All right, but we can't, with an interval, deal with this situation, right? Because if we did our interval like this, both of these would be negative. Okay? Likewise, here, both of these would be negative. So we can't get this negative, positive, negative. Sorry, positive, negative, positive. All right, so let me skip this just in the interest of time because I'm running over. So much more interesting, of course, to us is the linear decision boundary, because almost everything we care about is a linear decision boundary. So I'm going to tell you that the VC dimension of a linear decision boundary is got to be greater than 3, because here are 3 points, and I can draw my line to separate those two, okay? Or I can draw my line to separate those two away, or whatever, right? I can choose any of these lines, and as long as I can run any of these lines, I can do every combination of positive and negatives, okay, for every pair. But it can't be more than 4, because I can set up these situations where essentially there's every possibility here with 4 points, okay? If we have 4 points, either 3 points define a triangle. Okay. So a triangle is also known as a convex hull. And a convex hull means that there's going to be an interior location, like there's something inside a triangle. So there's only two possibilities, right? That you either have a situation where the fourth point is inside the triangle, right? Or it's not. Right? And in the case of that, then we have something like this, right? So all points lie on the boundary of the convex hull in the case of a square or a rhombus or whatever. Okay? So this is our familiar exclusive OR problem. We know that you can't draw a line to separate out the red from the green, so that's a failure. And also when the point is inside, then there's no way to separate it from the others. You would need a circular boundary in order to do that. Okay, so both these cases fail. All sets of 4 points belong to one of these two cases, QED. The VC dimension of a line is less than 4. Okay, since it's less than 4 and more than 3, we know that in fact the dimension of a line is 3. And in fact, this generalizes. So if we have not a line in 2 space, but a line in M space, then the dimensionality of that is M plus 1. All right, I'm going to skip this is the same thing, but those will be in the slides. So that leads us to this formulation. All right, so the VC dimension is going to stand in, actually, I really want this to be red. So we're going to replace the size of the hypothesis space with the VC dimension. Okay, and the VC dimension of an infinite hypothesis space is just a definition which says this is the biggest set that it can perfectly split, or as the terminology says, shatter, so that all points can be played into whatever, it can be played into all possibilities of classification. Okay. So other than that, the two equations are the same. We just replace the dimensionality of H with the dimensionality, the VC dimensionality of H. And now we can once again have our bounds. Okay, and again, everything we care about is going to be over here. And to be honest, probably over here. All right, so we wanted bounds on how good learning can be, right? As I mentioned, there's lots of frameworks for doing stuff like this in different kinds of algorithms. The one we're giving you today is just an example of how this stuff works, okay? So things you should know. Statistical learning theory, which is this VC dimension stuff, is basically what led to the development of SVMs. So support vector machines come from Vapnik's work on VC dimension. After he did that, he came up with this, which takes the VC dimension to the next level. Okay, and as we noted, the VC dimension of an m-dimensional hyperplane is m plus 1. So we know the complexity of any SVM in whatever the dimensionality is. So negative of all this stuff is that these kinds of bounds are super loose. So if you read the Chris Bishop book that I've said is our textbook that's available online for free, his section on this kind of learning theory, he questions the real world usefulness of these bounds because they're so loose. If you think back to that proof, there were 3 or 4 times we took a bound that existed in a tighter form and we made it looser so that we could get to an analytic solution, essentially. So, but hey, it's still important to have some idea of the number of samples that you need to get perfect or close to perfect error. And that's nice. Even if they're very loose, it's better than nothing. So importantly, right, what we generally care about are, in this kind of learning theory, is we like to know that learning is even possible, that learning of certain kinds of classes is possible, and if we can get to a guarantee like this, which is not just that it's possible, but how many samples we need to do it, that's pretty good. All right, so that's all I had for you today. I'm well over time. I apologize for that. But next we're going to take this kind of stuff and show you that it motivates cross-validation and regularization, and talk about how we can do model selection using cross-validation. All right, but all that is going to be, I think, Wednesday, if I've got my head on straight right now, because Monday, again, we're going to do an exam review. So that's it. Bye for now. Have fun.